First problem set for integrals. Page 1. Area under curve. Remember in the investigation that you counted up those little squares underneath the curve to estimate the area. You can do a more exact calculation by drawing little rectangles underneath the curve. Okay, so there's two ways to draw the rectangles. There's this method, which draws the rectangle so that the height corresponds to the maximum value of the function in that interval. And there's this method, which does the opposite. It makes the height of the rectangle equal to the minimum value of the function within the interval. This technique here is called upper rectangles, and then this technique here is called lower rectangles. The area A sub L created by lower rectangles is less than the actual area A, and the area A upper created by the upper rectangles is greater than A. I should probably say equal to. Less than or equal to, greater than or equal to. By gradually reducing the width of the rectangles, both area approximations will converge to the actual area. Around 200 BC, the Greek philosopher Archimedes, this is in the book, calculated the exact area under the curve y equals x squared between x equals 0 and x equals 1. That's pretty impressive considering he didn't have calculus yet, right? Consider the area between y equals x and the x-axis from 0 to 1. Let's draw a little graph just to see what that looks like. Y equals x, if you remember, is a straight line at a 45-degree angle. Looks kind of like that. The region from x equals 0 to x equals 1 is from here to here. They want to know how much is this area here. Okay, from 0 to 1. Divide the interval into 5 strips of equal width, then estimate the area using upper rectangles and lower rectangles, and then calculate the actual area and compare it with your answers in A. Well, to calculate the actual area, we can do that first. It's pretty easy, right? You got a triangle that has a base of 1 and a height of 1 also, and then it's a triangle, so it will be basically area equals 1/2. Right? And what they're asking us to do is to calculate it using upper rectangles and lower rectangles. So what you do to do that is you divide up this space into 5 sections like that. And in upper rectangles, basically you're making these rectangles here that match the height of the, let's see, the tallest point within the interval. And for lower rectangles, you do these green rectangles, which the height of the green rectangles matches the lowest. Okay, so let's see. What we can do is let's do upper first. And so what we'll do is we will we'll find the area of each little rectangle. From 0 to 0.2, that's the first interval, and for upper rectangles, we are talking about a height of, let's see, we're going to plug in the value 0.2 into y equals x, and so the height is 0.2, and the width is also 0.2. So it's 0.2 times 0.2, which is 0.04. Okay, what about the interval from 0.2 to 0.4, which is right there? The height would be 0.4, and the width would be 0.2. So that multiply that together, we get 0.08. What about from 0.4 to 0.6? The height would be 0.6, and we would multiply that times a width of 0.2. So that would be 0.12. And so you can see the pattern here. The next one would most likely be 0.16, and the next one, the last one, would be 0.2. Okay? And then for the lower rectangles, the first one would be 0 because the height of the leftmost rectangle is 0. The second one would be 0.2 times 0.2, so it would be 0.04. So you can see that they're all shifted down like that. Okay, and then we could add these up, 0.48, 12, 24, 0.4. This one would be 0.4. And the red one would be 0.6. Okay, so we can see that the upper limit would be this, it's AU, and the lower limit would be 0.4. And the actual number, the correct answer is A equals a half, so it happens to be halfway in between those two. Okay? So, let's move on to number 3. Use rectangles to find lower and upper sums for the area between the graph y equals x squared and the x-axis for x between 1 and 2. Use n equals 10, 25, 50, 100, and 500. Give your answers to 4 decimal places. As n gets larger, both the area lower and upper rectangles converge to the same number, which is a simple fraction. What is it? Okay. And here I put a procedure for you to use on the calculator. I'm going to show you how to do that now. Let's see. We are going to first take n equals 10. Okay. And our limits are, let's draw a little picture here. You're going to have a parabola, y equals x squared, and let me draw a little bit more steep. Okay, so the points we're looking at are between x equals 1 and x equals 2, so that would be height of 1 here and height of 4 here. And we're looking at this area here. And so the first thing we're going to do is we're going to divide it into 10 rectangles, and then we're going to divide it into 25, 50, 100, and 500. And for each one, we're going to get a different AL and AU. I just made a little chart here to fill our answers in. Let's start with n equals 10 and figure out AL and AU for n equals 10. So I'm going to just draw a little picture of a rectangle for one of these here. So let's do the AL rectangle. So the AL rectangle is width 1 over n times, or 1 over n is the width, and then the height would be, let's see, an x squared. Okay, and the way we do this is we are going to make an expression for like each one of these rectangles. It's like a general expression. So all these areas can be expressed as x squared divided by n. Now, what's x going to be equal to? Well, for the first rectangle, it's going to be equal to 1 squared. And for the second rectangle, it's going to be, if this is 1, this is going to be 1.1. So it's going to be 1.1 squared. And the next rectangle is going to be 1.2 squared, etc. And the way the calculator generates the 1 and 1.1 and 1.2, etc., is it does it with whole number counters. So like to generate the 1, the 1.1, and the 1.2 with whole numbers, what we need to do is start it with like, we're going to do 10 divided by 10, and 11 divided by 10, 12 divided by 10, etc. And we're going to go all the way up to 1.9, so 19 divided by 10. So the counter is going to be 10, 11, 12, 19. And then we're going to divide the counter always by a 10 so that we get the decimal number going up. And this is kind of hard to understand. So here's the instructions right here. We're going to do the first one, and then maybe you'll understand from the first one how to do the others. So first we go second stat, which is go to list, and then we're going to first get the sum, because we need to like say first, we're going to sum all of these rectangles. So we'll get that from math. Okay. Basically, we're building this command. Okay. And then we go to second list sequence, and sequence can be found in operations. For some reason, they put it in a different place. And then we're going to put the expressions here. And so, like I said, the first expression is going to be we're gonna figure out a way to generate the 1, the 1.1, the 1.2, the 1.9. And so the way we're going to do that is we're going to have a counter, which is x, and we're going to divide it by 10, and then we're going to square the whole thing. Okay, so we're going to have a counter, x, we divide it by 10, and then we square the whole thing. And we also would like to multiply this height with by a width, and the width is 1 divided by n, which in this case is 10. So we're going to divide by 10. So maybe what we could do is we could just put at the beginning, we're going to put 1 divided by 10 here. 1 divided by 10. Okay, and then, so that's the width, and then we multiply by the height, which is x divided by 10 squared, and the first x value is going to be 10. The variable is x, the start value is going to be 10, the end value is going to be 19, we're doing the lower rectangles, the step is going to be 1. So the answer is 2.185. So we'll put that in to our chart. Okay. And then what about the upper? What does that look like? So let's see if we can just edit this. It would be easier. So the upper is kind of the same. The difference between the upper and the lower is instead of doing 1, 1.1, 1.2, what we're going to be doing is 1.1 squared, and then we're going to be doing 1.2 squared, etc. So basically, instead of 10, 11, 12, what we're going to do is be doing 11, 12, 13, and the last one's going to be 20, right? So let's change this to 11 and 20, and everything else is going to be the same. Okay? Everything else is going to be the same for the upper. And we get 2.485. 2.485. Okay. How about if we do this with n equals 10? How does that work? Or n equals 25. So now we just need to change some of the counter values. So like instead of the the n value, so instead of 10 we're going to put 25. And then instead of this 10 we're also going to put 25. And then we do need to adjust these counters because now it's over 25. So now in order to generate the 1, we're going to have to put 25. And to generate the very, the 1.9 or the very last value, it's going to be, 50 minus 1, which is 49. Okay. So we get 2.2736. And it says 4 decimal places, so we want to keep all those. 2.2736. Okay, and then we want to go, oops. Okay, then we want to go up and grab that again, and this time we're going to adjust it so that instead of 25 to 49, now we're going to use the upper rectangle. So we're going to put 26 to 50. And then run that. 2.3936. 2.3936. Okay, so do you see how in the first one we used n equals 10, and then the counters we used 10 to 19, and then we used the counters 11 through 20 for lower and upper rectangles. And then for this one, we used 25 to 49 and 26 to 50 with n equals 25. So you can see the pattern here. We're going to be using, here we'll be using 50 to 99 and 51 to 100. For this one, we'll be using 100 to 199. And then here we'll be doing 200, we'll be doing 101 to 200. And for this last one, we'll be doing 500 to 999, and then 501 to 1,000. Okay? So, let's do a few of these. So here we're going to be doing n equals 50. So all the 25s we're going to change to, what do I keep going there? All the 25s we're going to change to 50. And the 26 and 50 we're going to change to 50 and 99. 50 and 99. And we get 2.3034. 2.2034. Okay, and then we're going to do our upper rectangles, which is going to be 51 to 100. And then we're going to put comma 1, close parentheses. 2.3634. 2.3634. Okay. Do you see the reason why we have these chosen counters here? Basically, what we want is to generate numbers between 1 and 2, but we want decimal numbers. But the calculator cannot generate decimal counters. It can only do a whole number counter. So you have to figure out what whole numbers you want and what denominator you need. And the denominator is also, it's going to be the n value. So the denominator is already determined. And then you need to figure out what whole numbers you want to count through it to generate the numbers you want. So for example, for 10, we wanted to count from 1 to 1.9 for the lower rectangles. And for the upper rectangles, we want to count from 1.1 to 2.0. And that's going to vary a little bit depending on the size of your rectangle, right? So let's go down to the n equals 100. We'll do here. And when we have n equals 100, and we can do a second insert here, it allows us to put in more characters here. So we only have space to put in one character. We'll do a second insert. We'll do 1, 0, and then we'll delete the 5 here. Or we'll just type over it. We'll put a 0. Okay. So now we have n equals 100, and then for n equals 100, our values are going to be 100 to 199, 100, comma 199, comma 1. The 1 is the step, and then we do enter. 2.31835. 2.3184. 2.3184. Okay. And then we go up and grab the next one, and then we're going to put 101 and 200. Okay. 2.3484. 2.3484. And you can see that we're converging to a value here. Last one. Now our n value is 500. So replace our n value there. Place our n value there. And so now our counter values are going to be 501 to 1,000, not 1,000. It's going to be 500 to 999, right? Jumping by ones. We might be able to use that jumping by ones to make our algorithm a little less complicated. That took a long time. 2.3303. 2.3303. And then finally we're going to do 501 to 1,000. 1,000, comma, 1. .3363. 2.3363. Okay. So it converges to the same number, which is a simple fraction. What simple fraction is it? Well, it's 2 1/3, which is the same thing as 8/3. Is that right? 7/3. Okay. All right, and that was page 1.